In this chapter, we will be studying quadratic functions. In this lesson, we will be determining the nature of the roots. And to do that, we'll introduce an expression called the discriminant.
Hi everybody. So in the last lesson that we went through together here, we were talking about how to use the quadratic formula to find the roots of a quadratic equation. Now we want to focus a little bit more specifically on what it is that we're actually doing when we solve for the roots. And we're going to take a look at the types of roots that you can get. Now you might not even have thought that there were different types of solutions that you could get to an equation. But there are, okay? And in fact, in the last lesson that we did, I tried to hint at the issue that we're going to address in this particular lesson here. So let's just take a look here. So the zeros of a quadratic equation are the x-intercepts of the graph. Okay, it's important that you make that connection, particularly now in this lesson here. Okay, so the roots of the equation, or the zeros of the function here, are going to be the x-intercepts of the graph. Now, to determine the x-intercepts, and we've done this before, you could do that by graphing. Okay, use your calculator, find the two x-intercepts, boom, you're done. You could do it by factoring. Once it's in factored form, remember each factor is going to identify a possible x-intercept. And then by using the quadratic formula, and we saw how that works to find both of them because you had the plus or minus the square root, and it was that plus or minus that gave us the two x-intercepts. Now, what we're going to do here is we're going to see if we can figure out a shortcut to determine how many, if any, x-intercepts the quadratic function might have. Okay? This is sort of hinting at a larger issue in mathematics. Okay? Throughout history, mathematicians have been looking for ways of solving equations, okay? But sometimes the issue gets a little bit deeper than after you get frustrated after a while if you can't find the solution. Sometimes the question then becomes, well, man, is there even a solution? It's like, am I wasting my time? Is there even an answer to this? If there is, then I'll keep working at it. But if there isn't, why am I wasting my time here? And so we're sort of going to come at it from that perspective. Is there even a solution? If there is a solution, well, how many solutions are there? But if not, then I'm just going to back off from that. So here's how we do it. We take a look at the quadratic formula, and if you remember in the last lesson here, I identified that there was some significance to the fact that the quadratic formula has a square root in it, because you can't always take the square root of numbers, right? If the number here is negative, if this part of this quadratic formula spits out a negative, well then you can't take the square root of it. We also discovered that if you were able to take the square root, if you got like if this was a perfect square, this b squared minus 4ac, if that was a perfect square, then you could have factored whatever that expression was. Actually, you could have found factors to make that work. Maybe you didn't see them, and that's okay. That's why you can use the quadratic formula. But if that is a perfect square, then that could have worked. We're going to see that this particular little expression right here is actually really important. We call it the discriminant, okay? Because it helps us discriminate between the different possible kinds of answers that you can get when you're solving a quadratic equation. Now, let's talk about what we mean by that. When we talk about the nature of the roots here, now I'm not going to be able to get the whole thing. I can actually, hold on. When we talk about the nature of the roots, there's really only three possible answers. When I ask you to describe the nature of the roots, there's only three, okay? No other answers here. So the equation could have real roots. Now, okay, that means it's going to hit the x-axis somewhere, okay? If there are real roots, okay, it crosses the x-axis, then you could have different or equal real roots. Okay, so in other words, it could do something like this. It could hit the x-axis twice. It could hit the x-axis once. That's what these are trying to say here. So you could have real roots, and then there's this subcategory. They're either different real roots or what we call two equal real roots. Now, I know this is going to seem a little bit weird here because here you've got two x-intercepts. Here you've only got one x-intercept. But there's a rule in mathematics, and it's called the fundamental theorem of algebra, that says if you've got a linear equation, you're going to get one solution. If you've got quadratics, you're going to get two solutions. If you've got a cubic, you're going to get three solutions. If it's a quartic, you're going to get four solutions, and so on. Okay, so whatever the degree of the equation is, that is the number of roots you're going to get. When you get a question like this is going to be a second degree equation. It's going to be quadratic, but you're only going to get one number that pops out as the answer. Now, graphically, that amounts to one x-intercept. But when you approach it from kind of an algebraic perspective, you'd kind of like that fundamental theorem of algebra to still hold. So what we say in this case is this has actually got two roots. They just happen to be the exact same number. Here, there are two roots that are different. If you think about your axis of symmetry, they're symmetrically spread about that axis of symmetry, one to the left, one to the right. Here, they both land right on that axis of symmetry. So here are two possibilities. And then the third one here is if the equation has no real roots. Okay? Now, it would be inappropriate to say that it has no roots. Yes, it does. It's just that they're not real. We're pointing towards another branch of mathematics that deal with imaginary numbers, okay? And that's when you take the square root of a negative. I know you've probably been told that you can't take the square root of a negative, and I've probably even mentioned that in the past there, but that's more of a statement of convenience than it is a statement of truth. Just earlier than this, we just don't want people concerned about that. And so when we say that, we're really implying that there's no real root. However, there are roots. Okay, so now what we want to do here is let's talk specifically about this discriminant here. So the expression b squared minus 4ac, we call that the discriminant. And just like the quadratic formula, you get it when you have the quadratic written in standard form. ax squared plus bx plus c equals 0. Okay? So how do we get the discriminant? And you should know this isn't going to be on your formula sheet. The quadratic formula will be. So you simply need to know where to look, where the issue is. And the issue is, and I'll just slide back up here again, the issue is under the radical. That's where all the real decisions get made right there. Okay, it's what's under the radical that either allows us to move ahead and find the solutions or back off, there is no solution. So first thing we're going to do is we're going to put our quadratic equation in standard form so that you can identify the a, b, and the c. Okay, and then you're simply going to substitute those in to b squared minus 4ac, and the value that you get is going to let you know what kind of roots you've got, whether you've got two roots, one x-intercept, or two, okay, think of it like, I should have said it like this, I should have just said it like this. Two distinct real roots, two equal real roots, or down here, no real roots. So we've got a little chart here on the next page to kind of help you deal with this. Whoops, wrong way. Okay, so the value of the discriminant, if it's greater than 0, if it's positive, okay, if it's any positive number, doesn't matter what it is, okay, any positive number, then we're going to have two different real roots, okay? Because there's going to be two different factors if you were to write that in factored form. Now, it might not be possible to write that in factored form in any kind of nice, concise way. You might have radicals in there, but just think about it like this. If this is the number 10, if b squared minus 4ac is 10, there is a square root of 10. It's not a nice number, okay? It's going to be an irrational number, but you can find the square root of 10, and you can add or subtract that to another number here, okay? You can use it. So what happens here is you would get this axis of symmetry that goes through the center, and then when you take that square root, that plus or minus square root, that's going to go forward that square root, backwards that square root from the axis of symmetry. That's not exactly what happens here because there's a little bit more to that calculation, but that gives you a rough idea of what's going on here. So as long as this is some sort of positive number, there you go. You're going to get two x-intercepts. And that might be another way of thinking about it here. You're going to get two x-intercepts. The second case here is if the discriminant is equal to 0. Okay? And that's kind of an interesting one here because, and this is going to throw a lot of people off here. What's the square root of 0? Now, I suspect out there are a lot of people thinking, wow, you can't take the square root of 0. But yeah, you can. The square root of 0 is 0. You can't take the square root of a negative and get a real number, but you can take the square root of 0. Okay? So the discriminant is equal to 0, and what happens here is you're going to get two equal real roots. Now the reason for that is, if you think about your quadratic formula, this now becomes negative b plus or minus, I'll talk about this in a second, over 2a. Where the discriminant would sit here, the discriminant would be 0. The square root of 0 is 0. So then you're left with two options here. Either it's going to be negative b plus 0 over 2a, or negative b minus 0 over 2a. Now that plus or minus 0 does nothing to that expression. Basically, they both reduce down to negative b over 2a. You're going to get the same result either way. That's why we call those two equal real roots. I'm getting it in two different ways, but I'm getting the same result either way. This results in a single x-intercept. And in fact, if you think about it here, normally it would be negative b plus or minus. So up here it'd be like my axis of symmetry plus or minus that value. Here, I'm adding and subtracting 0. I'm not going anywhere, which is why my root is right on that vertex, that axis of symmetry. So we're going to get one x-intercept if this is the case. And then our final case here is if the discriminant is less than 0, is negative. Okay? And in this case, there's no real roots because that discriminant sits underneath the radical symbol. If this is a negative number, okay, the square root of a negative number is going to be an imaginary number. There are no, now when we say here there are no factors, that's a little bit of a misnomer here. There are, it's just that we're now entering the imaginary or the complex number system here. And that's not what we want here. Essentially what that means is there's no real roots. There's no real x-intercepts because when there's no place where we can hit the x-axis. Any number that we hit the x-axis on right here, any number that we intersected at, is going to be a real number. So what's happening here is there are none, so we must be up above or completely below the x-axis here. There are no x-intercepts here. Okay, now I hope that makes sense. It gives you a little bit of insight into the behavior of the quadratic, even before you start and specifically find the x-intercepts here. Now let's take a look at some examples. So in these next few questions, we're going to use the discriminant to determine the nature of the roots. So we're going to figure out what they're going to look like even before we actually get to the what the roots actually are here. So this is written in the right form here. So b squared minus 4ac. Okay, this is going to equal negative 1 squared minus 4 times a times c. Now it's really important that you put that negative in parentheses here. Now, although in this particular case it's not going to make that big of a difference, it's not going to change the answer here, but it can change the answer if you do that incorrectly. So negative 1 squared is 1. And then minus 4 times 3 is going to be negative 12 times 4 is negative 48. 1 minus 40 is going to be negative 47. Now it doesn't really matter what the value is, it's what the sign is. Because this is negative, there's going to be no x-intercepts here, or no real roots. Or if you want to think of it like this, another way you could write it is you could say that there's two non-real roots if you really want to be accurate with that. Yeah, there are roots, they're just not real. Over here, our discriminant, okay, our b squared minus 4ac is going to equal, again, negative 1 squared minus 4 times 1 times negative 5. Okay, negative 1 squared will be 1. Negative 4 times 1 is negative 4 times negative 5 will be 20. So 21. Now that's a positive number. That's a positive, so that means that I could take the square root of that. So I'm going to get two distinct real roots. Okay? I am going to get a square root of that, so I am going to be able to add that number and subtract that number from the axis of symmetry to get two real roots for that. Awesome. And in this last one here, again, b squared minus 4ac is going to equal, here, negative 12 squared minus 4 times 4a times c. Negative 12 squared. Now in this case here, that negative, that's important that I deal with that. This is going to end up being positive 144. And then negative 4 times 4 is going to be 16. Then times that 9 is going to be negative 144. So we get 0 as our answer here, which means we still have 2, but we have 2 equal real roots. Okay? So this is going to be 1 x-intercept if you want to think about it like that. Because in this case here, again, the square root of 0 is 0, so we're adding nothing and subtracting nothing to the axis of symmetry. So there's going to be no change with that. Okay, we got one more question here, and actually, I'm really glad that a question like this is here in this workbook. We're seeing more questions like this pop up on exams and whatnot. So we're going to describe the nature of the roots of the quadratic function in vertex form. So bear in mind, we're looking at it in vertex form. So we've got the a times x minus p squared plus q. So now here's the scenario here. A is positive, p is positive, q is positive. Now let's bear in mind what this is saying. Okay, p is positive, meaning that this quadratic has been transformed to the right. P units, don't know how much that is, but p units to the right, and then q units up. So p to the right, q up is going to put us, let's say, somewhere here. I don't know really where, but I know it's going to be in quadrant 1. If the a value is positive, bear in mind we know what that means. That means we know that this parabola is going to open up. Now, it doesn't hit the x-axis, so what do we know about the nature of the roots? Well, we know that we've got two non-real roots. Okay, two non-real roots. Doesn't hit the x-axis, that's what's got to be going on. Okay? Here, p is equal to 0, meaning that there's been no translation left or right. Okay, but q is greater than 0, so we go up. So I know it's going to be right on the y-axis. I'm sorry, I want you to see that a little bit better. Right on the y-axis, and then we know that a is less than 0, so it's going to open down. Now, I am hitting the x-axis at two distinct parts here, which means when I ask for the nature of the roots, we are going to get two distinct, okay, real roots. Now, without even trying, I can probably guess that the next one's going to be two equal real roots, but let's just take a look at this scenario anyway. A is greater than 0, doesn't really matter. P is less than 0. Okay, P being less than 0 means that this quadratic has been translated to the left. I don't know how far, but to the left. Q equals 0 means it's not going up or down. It's staying right on the x-axis. Now that's significant. That means that the vertex is right there on the x-axis. So I know right now, regardless of which direction it opens, it's only going to hit the x-axis once. In this case here, because A is positive, it does open up. But I can see that it's only going to hit the x-axis once. So in terms of the nature of the roots, I've got 2. Remember, it's always 2. With a quadratic, we're always going to get 2 roots, but these are going to be 2 equal real roots. Good. Really good kind of question for an exam. Anyway, I hope that helps. Hope that makes sense.